In the last video, we developed the idea, or we talked about the idea, of the force of gravity as long as you are at or near the surface of the Earth being equal to mg, where m is your mass and little g is the acceleration due to gravity. This g should be a subscript. It looks kind of funky, but this is f sub g. Matter of fact, let me write that a little bit more clearly. I'll use a capital G. F sub g, the force of gravity. Okay, so, and of course, what we said is that this is an approximation at or near the surface of the Earth. We're actually going to see in a few weeks when we talk about the full form of the gravitational force where this comes from. But I want to talk about something your book says. If you're in my class, we're in the OpenStack textbook. This says that is equal to your weight. And to be explicit, these should all be vectors. And there are a lot of people who take this approach. You'll find a lot of people who are smarter and more educated than I am that would say this is true. But this is not how I was taught, and this is not how I think about it. I actually just flatly think this is wrong. Why is that? Because your weight changes. And some would say your apparent weight changes. I'm just not that guy. I say your weight changes. Now, of course, and the reason why this can't be true if it's going to change is because this is a constant as long as we're at or near the surface of the Earth. Think about maybe the last time you were on a roller coaster, if you've ever been on a roller coaster. So you're here. Yay. Your arms are in the air. I'm not sure why you're standing up. It's a bad strategy, but you do you. So as you start to go up this hill, right? Think of, you were coming down and now you're going up. There had to be an acceleration in the y direction. What is accelerating you? Well, the answer is there's a normal force from your seat that's pushing up on your seat to accelerate you upwards. So you're accelerating upwards. And what do you feel at this moment? You feel yourself pushed down into the seat. Or maybe you've been at a stop sign with someone who is particularly maybe not law-abiding, and they just floor it when you get out of the stop sign. This is not prescriptive. Please don't do it. I'm not advocating this by any stretch of the imagination, but we all have those friends. So if that happens, what happens? You feel yourself pushed back into your seat as the seat is pushing on you, accelerating you forward. So what is going on? Well, there were some that would say you feel pressed down because your apparent weight has changed. I actually say your weight has changed. Your weight turns out to be a function of your interaction with some sort of surface. In this case, it's the interaction of you with the seat on the roller coaster, and the truck or the car, it's you with the seat that you have there. A common term for this is pulling G's, right? How many G's did you pull? What that says is that you were subject to a force greater than gravity, and you experienced an acceleration greater than little g, and I would say that your weight increases. Let's look at this. Let's say that you are accelerating upwards. So here's you. Here's the force of gravity. And what is accelerating you upwards? Well, you're standing on something or sitting on something. And if you're accelerating upwards, then there has to be a net force in the upwards direction. So let's assume you're standing on a surface, and this normal force is pushing you upwards. Maybe you're on an elevator and the whole thing is accelerating upwards. That doesn't actually happen very much in elevators. They accelerate for a little bit, then go at a constant velocity. But let's just pretend that you're accelerating upwards and you have this normal force that's accelerating you upwards. So I have to draw the normal force bigger than mg. I usually draw it the same because I'm usually sitting still, but in this case it has to be bigger because there has to be a net force upwards if I'm going to accelerate upwards. Okay, well, let's call up positive in this case so that my acceleration is positive. What are the sum of the forces? Normal force minus mg is equal to ma. Normal force is then equal to m. I'll just go ahead and move this over and factor it out. A plus g. The normal force is your weight. That is what is pushing up on you. This is, we're going to investigate this more later. This is why astronauts really are weightless in space. It's not because there's no gravity. There absolutely is gravity in space. If you take nothing else from this class, take that there's gravity in space. But they are in a state such that they have they are in a state of free fall, and they can't actually, they're not being pushed on by any surfaces. which is why they are weightless and they can float around. It's not because there's no gravity in space. So in this case, look, your weight has gone up from what it normally is. Normally, if you're sitting still, your weight is mg, but now your weight is m times a plus g. Let's say you're accelerating downwards. So again, I'll call down positive for this one so that my acceleration is again positive for purposes of comparison. So sum of the forces is equal to ma. Well, if down is positive, I get mg minus normal force is equal to ma. If I work this out, I'm going to get n is equal to m times g minus a. And you can see that now I weigh less. You experience this instantaneously when an elevator starts moving down. You kind of feel your stomach lurch a little bit. Or on the roller coaster, you experience this here as you're cresting the hill. And here you weigh more because you're being accelerated upwards. Here you weigh less because you're being accelerated downwards. So I just wanted to point that out. I'm not going to use the term weight for mg. Your book does. If you do, I'm not going to hold it against you. I read that language just fine. As long as it's clear that what you mean by this is mg. I personally don't ever feel a need to do this. As soon as I write down the gravitational force, I write down mg, as long as I'm at any other surface of the earth. But I did want to point it out. I do actually have a point of disagreement with your book. Your book is fine. People that wrote it are probably smarter than I am, and that's totally fine. But I don't like how they characterize this. But if you have been taught to do that and you want to do that, that's fine. For my money, just go to mg for the force of gravity, and all will be well.